I'm Siddharth Kaul and I welcome you to Edupedia World. In this video, I'm going to talk about memory usage in Matlab. We will discuss how to allocate and manage memory and use it efficiently in our Matlab programs. The video has been divided into 4 sections. The first section will deal with the memory allocation. Second will show the functions that are available in Matlab for memory management. In the third, I will provide some information regarding strategies to implement more efficient memory usage. And in the fourth, I will talk about how to resolve out of memory errors. I will start by memory allocation. So this section is slightly theoretical that will inform you how Matlab allocates memory for arrays and structures. The purpose of this section is to inform you about the internal operation that goes on in the Matlab. You need not be aware about this, but this information do help in writing more efficient code memory-wise. Now, creating and modifying arrays. So, when you assign a numeric or character array to a variable, Matlab allocates a continuous virtual block of memory and stores the array data in that block. Matlab also stores information about the array data such as its class and dimensions, but this is stored in a separate, smaller block of memory called a header. If you add new elements to an existing array, Matlab expands the existing array in memory in a way that keeps its storage continuous. This usually requires finding a new block of memory large enough to hold the expanded array. Matlab then copies the contents of the array from its original location to this new block of continuous memory and adds the new elements to the array in these blocks, and it also frees up the original array location in the memory. So if you remove elements from an existing array, Matlab keeps the memory storage continuous by removing the deleted elements and then compacting its storage in the original memory location. Working with large data sets. If you are working with large data sets, you need to be careful when increasing the size of an array to avoid getting errors caused by insufficient memory. If you expand the array beyond available continuous memory of its original location, so Matlab must make a copy of the array and set this copy to the new value. During this operation, there are two copies of the original array in the memory. So this temporarily doubles the amount of memory required for the array and increases the risk of your program running out of memory during execution. So it is better and it is recommended to pre-allocate sufficient memory for the largest potential size of the array at the beginning of the program itself. Copying arrays. In this slide, I will give you a brief explanation on what goes behind the scenes when you copy array from one variable to another. Internally, multiple variables can point to the same block of data and can share the same array value. So when a copy is made to another variable like b is equal to a, Matlab makes a copy of the array reference but not of the array itself. So as long as the contents of the array is not modified, there is no need to store more than one copy of it. But if you do end up modifying the copy, then Matlab makes a copy of the array and then it modifies that copy. This concept is explained in the example that has been presented here. Here first I am getting how much memory is being used by me as a user and by Matlab process I am currently running. So using memory usage I am getting this information. Now I will create a 2000 by 2000 numeric array A using magic function that will approximately use around 32 MB of memory. So from 295 my memory will rise up to 327. I will now make a copy of this array A in array B. As there is no need to have two copies of the array data, Matlab only makes a copy of the array reference. This requires no significant additional memory. So you can see that memory still remains at 327. Now I will modify this B by making it one half of its original size. That is set 1000 rows to empty. This requires that Matlab do make a copy of at least first 1000 rows of A array and copy it to B. Now I will check my memory again. I can clearly see that the memory use has increased by close to 16 MB to 343. This happened because of my modification of B that forced Matlab to create a new copy of for B, as B could no longer remain as just a reference to A. So this is how basically your copying works at the back end of Matlab. When you assign an array to a variable, Matlab also stores the information about the array. This information is like class and dimension of the array, but this is stored in a separate place of memory called a header. For most arrays, the memory required to store header is basically very insignificant. There is a small advantage to storing large data sets in smaller number of larger arrays as opposed to a large number of small arrays. This is because the former configuration requires very few array headers. For structures and cell arrays, Matlab creates a header not only for each array but also for each field of the structure and for each cell of a cell array. Because of this, the amount of memory required to store a structure or cell array depends not only on how much data it holds but also on how it is constructed. For example, take a scalar structure array S1 having fields R, G and B. Each field of size 100 by 50 requires one array header to describe the overall structure. One header for each unique field name and one header per field for 1 by 1 structure array. So this makes total of 7 array headers for the entire data structure. So this looks something like this: s1.r that has size 100 by 50, s1.g that has size 100 by 50, and s1.b that has size 100 by 50. So on the other hand, let's take a 100 by 50 structure array S2 in which each element has a scalar field. So only one element will be stored in it. So here the fields again remains the same, that is R, G and B. So in this case you need one array header to describe the overall structure and one for each unique field name and one per field for each of the 5000 elements of the structure, making a total of 15,004 array headers for the entire data structure. So this data structure looks something like this. So S2 100 by 50, that is the size of S2 for R, then again S2 100 by 50 for G, S2 100 by 50 for B. So even though S1 and S2 contain the same amount of data, S1 uses very less space in memory. Not only less memory is required, but there is corresponding speed benefit as well in the S1 format. S1 is much more faster to access as compared to S2, and S1 has very low memory usage as compared to S2. Memory usage in function argument is somewhat similar to the concept that is there in copying arrays. When you pass a variable to a function, you are actually passing a reference to the data that variable represents. So as long as the input data is not modified by the function, the variable in the calling function and the variable in the called function point to the same location in the memory. But if the called function modifies the value of input data, then Matlab makes a copy of the original array in a new location in memory. Then it updates that copy with the modified value and points the input variable in the called function to this new array. In the example shown, function myFunction modifies the value of the array passed into it. Matlab makes a copy in memory of the array pointed to by A, sets variable x as reference to this new array, and then sets the one row of x to 0. The array referenced by A remains unchanged. Array A, a magic array of size 500, and is passed to the function myFunction as x. The changes are done on x, but array A remains unchanged. If the call-in function needs the modified value, or you need the modified value of the array that was passed to myFunction, you need to return the updated array as an output to the called function. This is also shown here. So in the second code snippet, after changing the value of x, we are passing it back as an output argument, hence getting an updated array in array A. Memory requirements differ for the different types of Matlab data structures. Using this info, you might be able to reduce the amount of memory used by these structures. First, the numeric arrays. Matlab requires 1, 2, 4 or 8 bytes to store 8-bit, 16-bit, 32-bit and 64-bit signed and unsigned integers respectively. For floating point numbers, MATLAB uses 4 or 8 bytes for single and double types. To conserve memory when working with numeric arrays, MathWork recommends that you use the smallest integer or floating point type that contains your data without overflowing. Then the second is complex arrays. MATLAB stores complex data as separate real and imaginary parts. If you make a copy of a complex array variable and then modify only the real or imaginary part of the array, MATLAB creates an array containing both real and imaginary parts. Then comes the sparse matrices. It is best to store matrices with values that are mostly zero in a sparse format. Sparse matrices can use less memory and might also be faster to manipulate than full matrices. You can convert a full matrix to sparse format using the sparse function. Let's compare a 1000 by 1000 matrix X, that is a matrix of doubles with 2/3 of its elements equal to 0, and Y, a sparse copy of X. The example on the screen shows that the sparse matrix requires approximately half as much as memory. When we using the function whos, we get the size of X and Y. We see that the 1000 by 1000 array of X has close to huge number of like 8 million bytes of data, whereas 8 MB of data. Whereas the Y, that is a sparse matrix, but again the same size 1000 by 1000 takes only 4 MB of data. Memory allocation for cell arrays. In addition to data storage, cell arrays require a certain amount of additional memory to store information describing each cell. This information is recorded in a header, and there is one header for each cell of the array. You can determine the amount of memory required for a cell array header by finding the number of bytes consumed by one by one cell that contains no data. Let's find this. I have created an empty cell array A, and using whose function I will find out the size and bytes. Here the bytes shown on the slide are the bytes required for each header in cell array for a 32-bit system. The number required is 60. So this is the header size that is used in all of the example made in the 32-bit system. For a 64-bit system, the size is close to 112 bytes approximately. You can check it on a 64-bit system to get an exact value. Now to predict the size of an entire cell array, we multiply the number, that is this, by the total number of cells in the array, and then add to that number the number of bytes required for the data that you intend to store in the array. So it is like header size into number of cell plus the data. So a 10 by 20 cell array that contains 400 bytes of data would require 12,400 bytes of memory on a 32-bit system. So it will be like 60 into 200 plus 400, that is 12,400. In this second section, I am going to list out and briefly discuss the functions that will help in managing the memory use while running the Matlab. There are certain handful of functions that allows us to manage memory in Matlab. So I have summarized those here in this slide. The first is the memory function. It displays or returns the information about how much memory is available and how much memory is used by Matlab. This includes the following. It includes the size of the largest single array Matlab can create at this point of time. It also includes total size of the virtual address space available for data. It includes total amount of memory used by Matlab process for both libraries and data. It also gives the information about available and total virtual memory for the Matlab software process. It also gives information about available system memory, including both physical memory and the paging file. And it also provides information about available and total physical memory of the computer. Second is the whos function. That shows how much memory Matlab has allocated for variables in the workspace. Point to note is that whos does not include information about memory used by Matlab, that is for example Java code and plots and all those things. It also does not give information about memory used for most objects like time series, custom objects and all those things. And it also does not give information about variables that are not in the calling workspace. Then we have a pack function. So pack function saves the existing variables to disk and then reloads them continuously. This reduces the chance of running into problems due to memory fragmentation. Fourth is the fourth we have management function as clear function. It basically removes variables from memory. So this is one of the ways to increase the amount of available memory is to clear all the variables that is not used or no longer is going or is no longer used. So if we use pack and there is still not enough free memory to proceed, then you probably need to remove some of the variables that are no longer required from the memory. So we you can use clear to do this. Then then there is the save function that selectively stores variables to the disk. This is useful technique when you are working with large amount of data. You can save the data to the disk periodically and then use the clear function to remove the saved data from the memory, use that memory for something else and then reload the data. Then sixth is the load function. It reloads the data file saved with the save function. And the seventh and the last is the quit function that exits the Matlab program and returns all the allocated memory to the system. This is a very useful command in Unix system which does not free up memory allocated to an application until the application gracefully exits. Here in this third section, I will discuss some known strategies for efficient use of memory. These are kind of general and apply to Matlab as well, and I will also point out how it applies to Matlab. The source of many out of memory problems often involves analyzing or processing an existing large set of data stored in a file or in a database, and this requires in bringing all or part of the data set into the Matlab software process. So this slide points out the techniques that deal with minimizing the required memory during this stage. First is obviously load only the amount of data that you need. When working with a database, this is not an issue as you can query and get the selected data. But when working with large set of text files and MATLAB files, you can use appropriate function to achieve this. In mat files, you can load part of a variable by indexing into an object that you create with the mat file function. For text file, you can use the text scan function to access parts of a large text file by reading only the selected columns and rows. Moving on to the second way of reducing the amount of memory, it can be done by processing data by blocks. Block processing is something like processing a large set one section at a time in a loop. This helps as it reduces the size of the largest array in a data set. It also reduces the size of any copies or any temporary copies that may be required during processing. Moving to the third way of reducing amount of memory required, it is to try and avoid creating try to avoid creating temporary arrays. Even if you need them, make it a habit to clear it after use. There are also numerous ways MATLAB allows you to work by not creating a temporary array. The fourth and the last one is to use nested function to pass fewer arguments to the function. One of the points that most people forget is that MATLAB makes a temporary copy of an input variable if the called function modifies its value. So when working with large data sets, this temporarily doubles the memory required to store the array, which causes MATLAB to generate an error if sufficient memory is not available. One way to use less memory in this situation is to use nested functions. A nested function shares the workspace of all outer functions, giving the nested function access to the data outside its usual scope. This way we can manipulate how many arguments we need to pass to the function and hence reducing the amount of memory that may be required. MATLAB provides you with different sizes of data classes such as double and unsigned integer. So you do not need to use large classes to store your smaller segments of data. For example, it takes 7 KB less memory to store 1000 small unsigned integer values using the unsigned integer 8-bit class than it does with double. If you just need to carry out simple arithmetic and you represent the original data as integer, you can use the integer class in MATLAB. In the list shown here, I have mentioned numeric classes. its memory requirement in bytes, and the operation that are supported. So we have a single data type that has 4 bytes that does almost most of the math. Then we have double data type that is 8 bytes that does all of the math. Then we have logical that only take 1 bytes, so it is used for logical and conditional operation. Similarly, we have 8-bit integer and 8-bit unsigned integer that also takes 1 bytes and can be used for arithmetic and simple calculations. Then we have integer 16-bit and unsigned integer 16-bit that takes 2 bytes, again for arithmetic and some simple logical functions. Then we have integer 32-bit and unsigned integer 32-bit that takes 4 bytes that again can be used for arithmetic and simple operations. Then we have integer 64-bit and unsigned integer 64-bit that takes 8 bytes that again can be used for arithmetic and some simple operations. One of the most common errors that most people do are not storing data in the appropriate class. One classic example is when reading data from a binary file with fread function. It is common error to specify only the class of the data in the file and not the class of the data Matlab uses once it is in the workspace. As a result, default type of double is used even if you are reading only 8-bit values. The same has been demonstrated in the code snippet shown on this slide. A binary file has been opened in the first line. Then a read operation is done on the file mentioning that the file has unsigned integer 8-bit data in it. There is no mention of how Matlab should handle it. The data is loaded in variable A and the size turns out to be 8K. The same binary file has been read again by mentioning that the Matlab should also treat the data as an unsigned integer 8-bit. And now when we check the size, it becomes 1K. You can clearly see the huge difference between the sizes for the same data that has been imported. Matlab always uses a continuous segment of memory to store a numeric array. As you manipulate this data, however, the continuous block can become fragmented. When memory is fragmented, there might be plenty of free space but not enough continuous memory to store a new large variable. Increasing fragmentation can use significantly more memory than it is necessary. So there are ways to avoid this. First is to pre-allocate memory when creating arrays. In the course of a Matlab session, memory can become fragmented due to dynamic memory allocation and deallocation. The for and while loops that incrementally increases or grow the size of a data structure each time through the loop can add to this fragmentation as they have to repeatedly find and allocate larger blocks of memory to store the data. To make more efficient use of a memory, pre-allocate a block of memory large enough to hold the matrix at its final size before entering the loop. When you pre-allocate memory for an array, Matlab reserves sufficient continuous space for the entire full-size array at the beginning of the computation. Once you have this space, you can add elements to the array without having to continually allocate new space for it in memory. Matlab uses a heap method of memory management. It requests memory from the operating system when there is not enough memory available in the heap to store the current variables. It reuses the memory as long as the size of the memory segment required is available in the heap. It is recommended practice to first allocate the larger arrays and then the smaller ones for the optimum memory use. I will show you with a very simple example why. Consider the first segment of the code. It requires approximately 4.3 MB of RAM. This is because Matlab might not be able to reuse the space previously occupied by two 1 MB arrays when allocating space for a 2.3 MB array. First, variable A is allocated a memory of 1 MB, then B is allocated a memory of 1 MB. Then they are cleared. But then C is demanding 2.3 MB of memory. So even after clearing, Matlab may or may not be able to use the previous 2 MB of memory. But when inverse is done, like first variable C is first allocated 2.3 MB, then it is cleared and A and B are allocated 1 MB each, then total RAM memory utilization turns out to be only 2.3 MB as Matlab is able to reuse the previous memory left by the variable C. Moving on to this fourth section, I will suggest some methods of reclaiming memory and limiting memory and hence try to resolve the out of memory errors. The reason for this error could be actually the system is out of memory. Maybe it may also occur due to bad practices while allocating memory, and it may also arise due to too much reduplication of large data set. This section will highlight few ways in which you can free up space, reuse it, and probably avoid these errors. The Matlab software generates an out of memory message whenever it requests a segment of memory from the operating system that is larger than what is available. When a lot of these messages starts coming, so following are the general suggestion that Matlab suggests to reduce the frequency of these messages. First is to compress data to reduce memory fragmentation. Smaller the size of data, less fragmented the memory will be. Second, if possible, break the large matrices into several smaller matrices so that less memory is used at any given point of time. Third, if possible, try to reduce size of your data. Fourth step is to make sure that there are no external constraint on the memory accessible to Matlab. This happens for Unix system where you can use the limit command to check whether there is limit to memory that has been allotted to Matlab. Fifth is to increase the size of the swap file. We recommend that you configure your system with twice as much as swap space as you have RAM. Sixth and the last option is to add more memory to the system. So more the memory, more OS can allot to the program and to the Matlab. One of the biggest factors that limits the Matlab usage of large data set is the process limit. The process limit is the maximum amount of virtual memory a single process or application can address. On 32-bit system, this is the most important factor limiting the data set size. The process limit must be large enough for Matlab to store all of the data it is to process, then any Matlab program files it is running, the Matlab executable itself, and the additional state information. This process limit depends heavily on the type of operating system on which you are running the Matlab. So basically, if you have a 32-bit Windows 7 and higher, the process limit is close to 2 GB. If you are having 32-bit Windows 7 and higher with increased userware set, then you get a process limit up to 3 GB. For 64 bits Windows or Linux running a 32-bit MATLAB, the process limit is close to 4 GB. And when running 64-bit operating system, the process limit is up to 8 TB. You can verify the current process limit of MATLAB on Windows system by using the memory function that will return the maximum possible size of the array. The memory available for all the arrays, memory used by Matlab, and the physical memory available itself are also shown by this function. You can go through this data and you can come to know like what amount of memory is available with the Matlab and with your program. This concludes this video about memory usage in Matlab. In the next video, I am going to show you how to create custom help and documentation for your code or your toolbox or your program. So until then, please subscribe and thanks for watching.